we know that glucose is broken to release these end products to ATP, which is already net, because we had 4 ATP as the gross ATP production in glycolysis, and plus there were 2 molecules of ATP were being used up during the endergonic reaction. So we have these 2 ATP, which is already net. That is only in glycolysis. Now these 2 ATP can be used right away by cellular activities. On the other hand, we have 2 molecules of NAD that undergoes reduction. So we have 2 NADH and the 2 molecules of pyruvate as another end products. Now glycolysis is said to be anaerobic, meaning it does not use oxygen. So this occurs in the cytosol. Now, what is then the fate of these other molecules? Now, these 2 NADH will be brought to the cristae for electron transport chain. And the 2 pyruvate molecules will be brought to the matrix of the mitochondrion for Krebs cycle or citric acid cycle. Citric acid cycle. Okay. Now, let's discuss how these pyruvate molecules or these 2 pyruvate molecules will be broken or further broken down in citric acid cycle. Now, we have here pyruvate. So you have Acetyl-Coa and there is CO2 and there is FH. Then here the product or the products of this out of this pyruvate molecule breakdown, then that will be multiplied by 2 since there are 2 pyruvate molecules. Okay? So I have here. So the pyruvate enters into the matrix for, of course, that will be acted upon by this CoA, coenzyme A. So we have this so-called, this is step 1, condensation of acetyl-CoA with oxaloacetate. So when pyruvate is converted into acetyl-CoA, there is a release of NADH. So electron is released and is now trapped by the NAD, nicotinamide adenine dinucleotide. And of course, carbon dioxide is released. So that is decarboxylation. Pyruvate undergoes decarboxylation, meaning there is removal of carbon dioxide, and the result is the immediate intermediate product acetyl-CoA with the participation, of course, of this CoA. Now, it's the acetyl-CoA that enters the citric acid cycle. Now, the CoA is released. So citrate. So you have we are starting the step 1. So condensation of acetyl-CoA with oxaloacetate. So here, kay cycle man siya. So makondense na siya with oxaloacetate. And back here, the high energy thioester of acetyl-CoA is hydrolyzed. So there is hydrolysis that will happen, which provides the energy to drive step 1. So where is the source of energy to drive the step 1 or condensation of acetyl-CoA? You have here, this thioester acetyl-CoA. So that is acted upon by citrate synthase. So it enters now into the citric acid cycle. Okay. Now we have an allosteric enzyme citrate synthase is inhibited actually by the NADH, ATP, and the Succinate-CoA. So let's continue on step 2, which is dehydration and rehydration. When we say D means removal, hydrogen. Re means addition. Catalyzed by aconitase gives the isocitrate. So citrate will undergo dehydration and rehydration to produce isocitrate. Isocitrate, okay, you have there the aconitate or the cis-aconitate. Okay, so you have here 4 possible stereoisomers. So citrate is now converted into isocitrate. Then there is what we call as oxidation again of isocitrate, followed by decarboxylation. There is again removal of carbon dioxide. So isocitrate to be converted into alpha-ketoglutarate. So this is catalyzed by isocitrate dehydrogenase. Now, isocitrate dehydrogenase, that is an enzyme which inhibits ATP NADH, and it's activated by ADP and the NAD, which is an oxidized form. Okay, so isocitrate to alpha-ketoglutarate. Of course, there is carbon dioxide release here. There's another carbon dioxide. Then step 4 is the oxidative decarboxylation of alpha-ketoglutarate to succinyl-CoA. So alpha-ketoglutarate to succinyl-CoA. Here, there is again release of carbon dioxide. Alpha-ketoglutarate will form now an intermediate product called the succinyl-CoA. So you have here with the release of carbon dioxide. Acetyl-Coa to Succinate. Now here, there is generation of ATP. First, guanosine triphosphate. But later on, this GTP will be converted into ATP. This is still energy currency. No? So what is different here, it's not adenosine, it's guanosine. No? Guanosine. So you have here, so that this, okay, this is energy yielding step. And of course, the GTP is produced. So this is now the energy. So Succinyl-CoA to succinate. And what else? Now, oxidation of succinate to fumarate. Now here, you have succinate to fumarate. There is a release again of electron or electrons. This time, the electrons are now accepted by another molecule, no longer the net, but it's the fat, flavine, adenine, dinucleotide. So you have here FADH2 production. So not like FADH2 production. So here, next step is hydration, meaning addition of water. Hydration of fumarate to malate or malic acid. So fumarate to malate. So there is, you have here the addition of water or hydration. Then step 8 is the oxidation of malate. So again, you have here malate is converted into oxaloacetate. Now oxaloacetate, of course, we have here the production or the release again of electron, which is trapped by the net. Nicotinamide, adenine dinucleotide is now reduced. So we have here another NADH. I'm inserting these important molecules, because they can still generate energy. You have the NADH, you have the FADH2. This ATP, of course, you have the GTP or the ATP, which is already used as energy for the cell. That is energy currency. And we have the oxaloacetate, which can react with acetyl-CoA to start another round by repeating step 1. So since there are for 1 molecule of glucose, it gives you 2 pyruvate molecules. So whatever is the product here, that will be multiplied by 2. So for, you have here glycolysis. Now for Krebs cycle, how many ATP molecules were produced? How many? 1. 1 times 2 equals 2 ATP. Then how many NADH were produced? In the citric acid cycle, we have 1, 2, 3, plus pyruvate to acetyl-CoA is 4. So you have 4 times 2 equals 8 NADH. Then how many FADH2? We have 1. 1 times 2 equals 2 FADH2. Now these 2 ATP can be used right away by the cell. However, this NADH and the 5H2 will be brought to the cristae for electron transport chain. So this will be brought to the cristae for electron transport chain. Okay, or for the generation. Yeah, but for the sake of computation, so we would know how many ATP production or how is then the total ATP production out of 1 glucose molecule breakdown, then we are showing it there. But actually, this ATP can be used right away by the cell. But we will compute later on as to what is really the total ATP that would be generated out of one glucose breakdown. Okay? So we have here the overall reaction of the cycle. Of course, there are carbon dioxide, we have GTP, we have 3NADH, excluding this one, and you have one molecule of 5H2. Of course, you have the protons. So that is the overall reaction for the sulfuric acid cycle.